Okay, so last time we started discussing the composition of stars, and I gave you the results already, that basically all the stars like our sun consist roughly 3/4 hydrogen, 1/4 helium, and small percentage of all other chemical elements. Now to understand what it all means, I started discussing a little bit the nature of ordinary matter, the stuff we are made of, and other objects around us. It's made out of atoms. Here is the lightest one, hydrogen, then the next heavier one is helium, and so on. Each atom has a nucleus, which is composed of protons and neutrons in general case. Each proton carries a positive charge. And in normal state, atoms are electrically neutral. That means that there are electrons, negatively charged particles, much lighter than the protons, 2,000 times lighter than the protons, moving around the positive nucleus so that the whole unit is electrically neutral. So, I mentioned that what is holding the electrons bound to protons is the electrical force, which, just like the force of gravity, varies with distances 1/distance squared, but it's much, much stronger than the force of gravity. It's stronger by a factor of 10 to the 36. So then, when you account for the properties of atoms, you don't need to take into consideration the force of gravity. Now, you can ask the question, okay, I told you that positive charges are attracted to negative charges and vice versa, and that the like charges, like those carried by protons, repel each other. So you can ask the question, well, what is holding together the nucleus? If these protons in the nucleus repel each other, how come that the nucleus is stable? How come that it does not fall apart? Well, it turns out that there is another fundamental force of nature, so-called strong nuclear force, that keeps nucleons together. It is much stronger than the electrical force, 100 times stronger, but it's short-ranged. It acts only over the distance equal to a diameter of a proton, which is about 10 to the minus 15 meters, okay? So the electrical force binds the electrons, which carry negative charge, to the positive nucleus, and then in turn, the nucleus is kept stable by the strong nuclear force that acts between any given proton or neutron and only its neighbors. It doesn't act over a long distance. There's another type of nuclear force, so-called weak nuclear force, that is responsible for so-called radioactive decay of some nuclei which are unstable, and they transform, and in the process there are particles that are ejected out of the nucleus, and it's the weak nuclear force that is responsible for that. So it is 100 times stronger than the electrical force, but it is short-ranged. It acts over a distance which is called 1 femtometer, which is basically 10 to the minus 15 meters, and that's 1/1,000,000th of a nanometer. So that is like taking 1 nanometer that we chose as a natural unit for wavelength of visible light, and you have then to divide it by 1,000,000. But so when the nucleus becomes too large, too big, what happens is that the nucleons that are on the opposite side of this large nucleus, they don't attract each other with strong nuclear force. But two protons on the opposite side of the nucleus still repel each other because the electrical force is long-ranged, right? So the big nuclei become unstable. And then it is sufficient to send in a slow neutron, for example, to break up the nucleus. And that's basically what nuclear fission is. And the first atomic bomb that was used in the Second World War operated on that principle of fission of heavy nuclei. So a little bit about the structure of matter. Now it turns out, as I mentioned earlier, that to describe the properties of atoms, we need a new type of mechanics, so-called quantum mechanics. Turns out that matter on these small scales behaves in a way that is very different from the way in which regular macroscopic objects like us behave. It's often very counterintuitive, and even experts are not always happy the way they understand it, but we all learn how to live with it. And of course, I'm not going to give you a course on quantum mechanics. I'm just going to tell you about some of its predictions that are relevant to us, to finding out about the composition, chemical composition of stars. So what quantum mechanics predicts is that one electron in an atom can be only in states of certain energies, which in turn depend on the chemical element involved. That is how many protons in nucleus it has. Okay? So electrons in an atom can have only certain discrete values of energy, and these values depend on the nature of the chemical element, that is, on the nature of the nucleus. Okay, so schematically, what the picture that one has, it is, if I plot on the vertical axis energy, E, energy, then in an atom, an electron can have energies of only certain values. So I'll denote them by these horizontal letters. So here is the lowest one that I'll call E0, then the one that is higher, I'll call it E1, then another one, E2, and so on. It is just like an apartment building with floors, but now the floors are not uniformly spaced, and each floor corresponds to a certain value of energy. So an electron can be in any one of these energy states. So say electron is in the state that has energy above the lowest possible energy. So this is what quantum mechanics tells us. The second prediction that it makes is that when an electron makes a transition from a higher energy state to the lower energy state, it emits a photon whose energy is precisely equal to the energy difference between the two levels. Okay, so schematically, if I have, say, electron in one energy level, say E1, and then it makes a transition, it jumps to the lower energy level, E2, the difference in energy will be emitted as a photon of electromagnetic radiation, and the photon energy, which, as you know, is some constant over the wavelength of the radiation, is precisely equal to the energy difference between these two levels. So this process, when the electron makes a transition from higher to lower energy level with the emission of photon, is called emission process. But there is also another possibility that actually a photon of light of just the right energy comes in to excite the electron to make it jump from lower energy state to the higher energy state. and that is so-called absorption process. Okay, so in this case, we have something that is opposite to what we had in 2, namely, again, I have energy here, right? So now it could be that the electron is in some energy state that I'll now call, I can call it again E1. And then the photon of energy that is precisely equal to the energy difference between this energy level and another one, E2, that photon comes in and its energy is absorbed by the electron, and it jumps, makes a transition to the higher energy level. And in this case, photon energy, which again is given by some universal constant of nature over the wavelength of the photon, must be precisely equal to the energy difference between the final energy state, in this case E2, and the initial one. Okay? So that's all of the quantum mechanics that we need in order to understand how astronomers determine the chemical compositions of stars.